Now that we found the dot product, we want to start looking at a couple of applications of the dot product. And the first thing that the dot product will help us find is the angle between two non-zero vectors. So basically what I'm saying here is if I were to have a vector here and a vector here, what would be the angle that is in between those two vectors? And the dot product is going to help us with that. So there's two ways that I can write a formula that will produce the angle measurement that these two vectors create. The first is if I write it in terms of the dot product, u dot v. The dot product of u and v is the same thing as me saying the cosine of an angle measurement times the magnitude of vector u and the magnitude of vector v. Now, that really doesn't help us because if I'm implying this, I'm getting the dot product from having the angle measurement. What we're going to use more often is if we manipulate this formula in terms of an angle. So let's get cosine of theta by itself, which means I've got to divide both sides by the magnitude of these two vectors. So if I want to find an angle in standard position between 0 and pi, I could say the cosine of theta is equal to the dot product of my two vectors, u and v, divided by the magnitude of the two vectors. And that's what we're going to use most of the time when we're talking about finding the angle between two vectors in standard position. So with this, we need to have the dot product, and we need to have the magnitude of u and the magnitude of v. So three pieces we need. So for example number 3 here, finding the angle between -2, 3 and 1, -5. So let's start by finding the dot product. I need the dot product, magnitude of u, magnitude of v. So if I do the dot product of u and v, it's taking the x components, it's taking the y components, multiplying them together, and then adding the result. So 2 minus 15, actually it should be a -2. We have -2 right there. So -2 minus 15 is going to be a -17. So then let's find the magnitude of u, which we know is going to be the square root of the x components plus the square root of the y component, which is going to be the square root of 13, 9 plus 4. And then finally, the magnitude of v, which is going to be squaring the x components and then squaring the y components, which will give us the square root of 26. So now that I've got the dot product, the magnitude of u and the magnitude of v, I can use my cosine formula. The cosine of theta is the dot product of u and v divided by the magnitude of u, magnitude of v. So if I substitute that in, I get -17 over the square root of 13 and the square root of 26. That isn't an angle measurement. I need to get that theta by itself. So then I'll take the cosine inverse of this expression. You don't need to worry about rationalizing because we're just going to plug this straight into the calculator. And if I do that, I get approximately 157.620 degrees. So that's my angle between those two vectors. The second example just has our vectors written as linear combinations. So the first thing I want to do right here is write it in component form if I can't do that conversion in my head. So this is going to be 2, 5, and this is going to be 5, 9. So once again, to find the angle between, I need to find the dot product. I need to find the magnitude of u and the magnitude of v. So first, the dot product, multiply the x's, multiply the y's, and add the result, which is going to give me 55. Magnitude of u is the square root of squaring the x component and squaring the y component and adding those results together, which will be the square root of 29. And then the magnitude of v, same idea, squaring the x's, and then we add the result of squaring the y's. It's going to give me 106. Now that I got those three pieces, I know the cosine of theta is the dot product of u and v over the magnitude of u and v. So 55 over the square root of 29, square root of 106. And then finally, since that's not an angle measurement, we'll take the cosine inverse of that expression. And if I plug that into my calculator, I get approximately 7.253 degrees. Now, that's all fine and dandy, but what does this give us? And this pattern is going to give us a real powerful concept. The idea of parallel and perpendicular vectors. And right here, this is probably the key piece. Two vectors are orthogonal. And orthogonal is just a term that means perpendicular when talking about vectors if the dot product is 0. And someone might say, well, why is it the case that the dot product is 0? Well, remember, the formula is the cosine of u dot v over the magnitude of u, magnitude of v. If I've got this dot product, u dot v is equal to 0, it doesn't matter what's in the denominator, because 0 over anything that's defined is going to be 0. And if I take the cosine inverse of 0, that's going to be 90 degrees. So that's why if I have a dot product of 0, I'm going to have two perpendicular vectors or orthogonal vectors. That's key. The second thing is if there is some constant that's the only difference between the two vectors, then we've got parallel. So for example 5, showing the two vectors are orthogonal, we just need to show that the dot product is 0. So the dot product of u and v, so multiply the x's, we'll multiply the y's, and then add the results. So negative 4 plus 4 is equal to 0. Right there, dot product equals 0. Thus, we are orthogonal. So the last question is, are the following vector pairs orthogonal, parallel, or neither? And for this, we've got to do a couple of things. We need to test for orthogonality, if you want to call that a word, which means we're going to check to see if the dot product is 0. If that's not the case, we'll check for parallel lines by seeing is there a constant that we can multiply or divide out. And if that's not the case, then we know it's going to be neither. So let's do a test for orthogonal. So I do my dot product, multiply the x's, multiply the y's, and then add the results. Well, I can see right here 15 times negative 5 is negative 75. 45 times 12 is not positive 75. So this is not going to be equal to 0. So we know it's not orthogonal. So then we're going to test for parallel. And the way we'll test for parallel is we'll see is there a constant between these two vectors. So let's just take one vector. I'll take 1545 and I'll divide it by negative 5, 12. And is there a constant that goes both between the x and the y's? Well, the answer is no. Because 15 divided by negative 5 is negative 3. 45 divided by 12 is not negative 3. If these were to have both been negative 3, I could say c is equal to negative 3, but it's not. Here, c we get negative 3 and 45 twelfths. So it's not parallel. So this is a neither situation. So last one here, example B. If I do my test for orthogonal, multiply my x's, multiply my y's, and then add the result, negative 16 and negative 4 is negative 20. So that's not orthogonal. So then we'll do our test for parallel. And our test for parallel, let's see, is there a constant that is the same through both of them? So 8 divided by negative 2 is negative 4. 4 divided by negative 1 is negative 4. So C is equal to negative 4, which means we've got parallel vectors. Now I could have done the exact same thing here by saying my negative 2, negative 1 is on the top, and then 8, 4 is at the bottom. And if I do that, I can see negative 2 over 8 is negative 2/8, which reduces to negative 1/4. And then over here I've got negative 1 over 4, which is negative 1/4, which shows me my constant is negative 1/4. I don't care what the C value is. All I care about is there some constant or some scalar that I can multiply through, and in that case it would be 1/4, but it still shows it's parallel. All I care about is the fact that it is parallel.